Binary stars, planets, and comets always trace a path that corresponds to one of the four conic sections. According to Kepler's first law of planetary motion, if two stars are gravitationally bound, their orbits are always either elliptical or circular. When a comet falls from a large distance with no initial velocity, the path is parabolic, whereas if a flyby occurs where the initial velocity is significant, the path is hyperbolic. Planets orbit in an elliptical fashion, with one focus in the center of the solar system's sun, and the other focus is generally just a point in space. We have never seen an open orbit, but it is possible that an object could approach our solar system from interstellar space and have the sun's gravity bend its path to curve around the sun and then return to interstellar space. This would cause the orbit to be a parabola or hyperbola, and would be an open orbit, meaning that it only goes around the sun once. The sun makes up 99.9% of the mass of the solar system, but the sun does have a slight movement itself because its center is not exactly the center of the solar system's mass. There are slight differences, but to within about 10 degrees, all the planets are in the same plane.
How long was that? It was discovered that planets actually orbited in an elliptical manner. Johann Kepler was a German astronomer who lived between 1571 and 1630. He introduced three important laws of planetary motion and helped the Copernican model of the solar system gain general acceptance. Kepler inherited Tycho Brahe's observational data on Mars following Brahe's death and showed mathematically that Mars followed an elliptical orbit. This new revelation contradicted the age-old belief planets moved in perfect circles, making him the first to correctly explain planetary motion. He brought about the acceptance of the heliocentric concept. That is, he believed the sun rather than the earth was the center of the planetary system. He was convinced that simple mathematical relations existed that could make sense of the planetary system. He saw the planetary system operating according to its own set of mathematical laws, which was quite a radical idea for those times. Kepler rejected many ideas, such as circular orbits, because they did not fit Brahe's observations. In 1609, Kepler finally published the first two laws of planetary motion in a book entitled New Astronomy. A decade later, 1619, his third law was published in the Harmonies of the World. Kepler then generalized, saying that his laws applied to all the planets, including the Earth. Today, we know they even apply to comets. The generalization of his laws predict and explain the motion of a satellite orbiting the Earth too. Kepler's work put to rest any notions that planets move in perfectly circular orbits, and also put to rest in the scientific community an ancient idea that exists a mystical, complex motion of planets that somehow governs our ways. Although Kepler never knew why planets moved by the empirical relationships articulated in his three laws, he sought a cause of which these three laws were the effect.
Because an orbit is an ellipse, or any conic, we can use its special mathematical properties to calculate things like the orbital period and the velocity magnitude of a certain celestial body. But first we have to know that r is simply the distance between the two bodies, and a is the semi-major axis of the orbit. And the semi-major axis is just half of the major axis. And mu is just the mass times the gravitational, it's just the mass times the gravitational constant. But why does this matter? Well, we've already established that an orbit is just a conic, and with these properties we can use them to calculate things like spaceflight paths, predict comet and eclipse appearances, and understand our entire universe in a new light. Yeah, that's it.
Ellipses have helped us orbit Earth. Essentially, there are two major orbit types for satellites. There are circular and there are elliptical orbits. Because of Kepler's work, the elliptical orbits of satellites are modeled after the orbits of planets going around the sun. Basically, gravity keeps the satellite velocity from sending the satellite flying out in a straight line away from Earth, and the satellite's velocity keeps the force of gravity from pulling the satellite back to Earth. This allows us to go into space, observe Earth from the outside in, conduct space research, and so much more. The use of ellipses in relation to satellites has opened up a world of new possibilities in further discovering space.